Thanks. Let's do a switch. It's more like kind of algorithmic theory talk, but hopefully with some legs in reality. So I'm going to talk about recent developments in cryptography, which really have I think, taken cryptography by storm. I think it's very exciting. I hope you'll think so too. So our story starts with the 80s childs, Alice and Bob, that in the 80s were, little kids in grade school, and they were very privacy-oriented. They wanted to talk privately without the teacher understanding what they talk about. And of course, they were using the recent technologies just came out in those times, public key encryption, Diffie-Hellman, RSA, probabilistic encryption in general. And they were very happy because they could talk to each other really privately without the teacher understanding what's going on. But really all they could do was just put messages in envelopes, in boxes, and send them to each other without doing anything else but locking and unlocking. And this was enough for them. But zoom in 30 years later, Alice and Bob are still very interested in privacy, but now they're adults, and their life is much more complicated because first they want to protect much more, but the computing environment is much more adverse in some sense to privacy because they don't really own their own computing devices that are fully self-sufficient. Everything is on the web, right? Whatever application they do, they have to do on the web, on untrusted cloud servers, right? All their data, the algorithms, the communication, everything is done in the open. Still, they are very privacy-oriented. So what do they do? And so, of course, cryptography rose to the challenge, and there are all these nice new mechanisms or algorithms or primitives, if you want to call it, that cryptography came up with over the years. Just to say what these are. So the idea is that cryptography came up with mechanisms to protect not just data, as in messages in transit, but actually to protect computations. So the computations themselves will be done in a way that is encapsulated. That we already heard talk, the recent talk about encapsulation, but this is not just encapsulation by programming. I'm talking about encapsulation that is resilient against even an adversarial machine that tries to see what's going on. So for instance, we have fully homomorphic encryption, which means that we can now take encrypted data and compute on the encrypted data such as the person who computes or the machine who computes has no idea what's inside, still to be able to compute it, get an encrypted answer. We can also do it in a verifiable way so that we can get offload our computations to the cloud, which we don't trust. The cloud will do the work. It can prove to us that the cloud did the work correctly, and we can verify it very efficiently. We have all kinds of fancy encryption that we are able to encrypt things and actually give somebody kind of a partial key that will decrypt only under some conditions, only some maybe parts of the message. All those things are very useful when you want to actually put data in the clouds and compute in it, and while preserving privacy. So we have all those things, and in fact, this new shiny tool that we have in the crypto toolbox is called program obfuscation, and this is what I want to talk about. It's kind of like pushes those things into an extreme. So what's program obfuscation? I'm sure many of you have heard about it. It's not a new thing. We know this for tens of years. Ever since we started programming, we wanted to actually be able to create programs that you don't really understand what's going on there. And either we want it or we do it just without wanting it, but still we do it. But the concept is really, really intriguing concept. How can you take programs and turn them into other programs that keep the same functionality, but are otherwise illegible, right? So in some sense, I want to be able to encrypt the program, but not really encrypt it, because I want the new encrypted program to still be useful. I can run it, but it's encrypted in the sense that I cannot see what's going on inside, right? So I want to be able to give you the ability to run it, to use it, to execute it, but I don't want to give you the knowledge that's associated with seeing the inside of the program. This I want to keep for myself. So how can I do it? So also, if you think about it from a theoretical point of view, it's kind of touches this idea of can we understand code in general. So we know we've learned that from complexity theory that you can't really understand code in general, can't really hope to understand code completely in general, all these impossibility results. But here I want to do something stronger. I want to be able to take any code, not just worst case code, any code, and algorithmically and efficiently turn it to another code which has the same functionality but is ununderstandable completely. Okay? So it's a much stronger form of that. And indeed, if I were able to do it, to take any code and encrypt it in such a way, there are lots of beautiful and great things we can do. And let me just try to give you some examples. So in general, first we can just take software and protect it from malicious modifications, from understanding my trade secrets, etc. It's great for software distribution. It also has some great cryptographic applications, which I'll mention in a second. So just as an idea for an example, so assume we have lots of medical data, which is very sensitive because it's privacy. It's private. It belongs to people. We don't want to reveal it, or we can't reveal it because of all kinds of flaws. But still, we want to allow drug companies to test things or to check things on this data, right? So what do? We want to allow the drug company to take this encrypted data, decrypt it, run all kinds of experiments on it, and then then also just get some piece of information from it that this piece of information, which is some aggregate computations, is not sensitive. But how can we let the drug company do it? How do we do it? We just give it the secret keys so that it decrypts and trust it to not to do anything bad with it. We don't want to do that. So one thing we can do is just give the drug company this program that decrypts, has the secret key inside it, decrypts the data, computes the computations for the drug company, give the drug company the OK output, and that's it. It doesn't give anything else. And we don't have to trust the drug company, we trust the program and the obfuscation that the only thing the drug company gets is what we allow it to get, just by obfuscation, right? Something else that we want to do, we have this suspect database that want to give all kinds of policemen or border control stations to see who is if there's a suspect person crossing the border. But we don't want to give the database out because it's very sensitive. So what can we do? We can actually, again, we can obfuscate it and give the border control station just the obfuscated program that matches the picture with the encrypted database and outputs yes if there is a match and nothing otherwise. Sorry. So this is another great thing that you can do with obfuscation, and there are many more. For instance, if I want to delegate a partial signing key to somebody, I want to give the cloud the ability, or somebody else the ability to sign something for me, but only for a certain day, only today, right? Only today I want you to be able to sign for me, but not tomorrow. So I can give you a secret key, and I can give you, but I don't want to give you a secret key. I could give you the secret key and with the program that says, sign only if it's today, or add June 2nd to every signature. But then I would have to trust you not to see the key. But instead, what I can do, I can just obfuscate it and give you the obfuscated program again. And now I have to trust the obfuscation. You cannot see inside it. And of course, you can think for yourself on more and more applications. So this is the idea. The question is how to do it. And in fact, before how to do it is what does it really mean? So we know that all of these software obfuscation software that is for sale out there, is for sale, right? We don't need cryptography for that. They're doing all kinds of randomization of address spaces, etc., etc. But all this, we know it doesn't really work. First, there's no rigorous guarantee that it works, and moreover, it's all being broken sooner or later. So those things don't really give any strong guarantee. But can we get something that has a strong guarantee? So in terms of what type of guarantee that you would like to get, so here's, first thing in cryptography that you do, before you actually try to do something, you try to define mathematically what it is that you want to achieve. And here is one type of goal that you would like to do. You want to say that, these are the guys that first studied this, take the code, you want to garble it, obfuscate it, and you want to have the guarantee that having access to the garbled code is essentially the same as having access to a black box. It just, on every input computes the output, right? So what I want to say, in other words, for every learner or adversarial user that gets the garbled program and tries to learn something from it, I want to say that this learner learns, whatever it learns can be done also by another guy, which I call the simulator, which the only thing that the simulator has is access to the program as a black box. Meaning just give it input, get output, input, output. So whatever I can learn with having access to the entire code, all the operations, but garbled, I could have done with just input, output, access to the program. Okay, so this is what I would like to do, and this is a very natural notion, and that was proposed. And indeed, there are all kinds of things that you can do with this notion. People have shown all kinds of specific types of programs, of functionalities that you can actually obfuscate using this program, but these are very limited. So I'm not going to go through this, but very specific types of programs. But the point was that although you can do it for specific things, there was an impossibility result. Actually, people showed that it is impossible to obfuscate programs in general, according to this notion. There are very general impossibilities that say that not just specific examples of things you cannot obfuscate, but essentially anything that you would like to be able to obfuscate, you can't really do it in a strong way like this. And this kind of went along together with this notion that all the existing obfuscation things, tools and algorithms that we have are broken. And people were thinking, okay, maybe obfuscation, it's a great thing to have, but maybe it doesn't really exist. Maybe we can't really do it. But then, several things happened more or less at the same time. So before this, there was this other notion of obfuscation that people suggested, which was much more modest. And let me just say what it is. The only thing that it requires is that if you have two programs that have exactly the same functionality, exactly the same input-output behavior on all inputs, right? And you obfuscate them, then the two obfuscated versions should be indistinguishable to you. So you give me the two programs, I obfuscate one of them at random and give it to you and tell you which one did I obfuscate, and you should not be able to tell the difference, even though you see the entire program. Okay, so this is a much more modest requirement than what I said before. It only applies to programs that have exactly the same functionality everywhere. But this notion did not have any possibility results. But it doesn't look very meaningful. And also, again, we didn't have any candidates, so people kind of brushed it aside. But then a couple of years ago, we figured out that it was a mistake, and this was what I said, this is generated this new excitement in cryptography. But two things happened in the summer of 2013. So first, people came up with a candidate obfuscator, and I'll say in a word what it is. It's an algorithm, it's kind of a compiler, a way to take any program and turn it into an obfuscated way in the way that I described. And the other thing that people discovered at the same time is that there's actually this weak notion of indistinguishability obfuscation that I described in the previous slide actually is very powerful. If you combine it with the right cryptographic tools, you can actually get a lot of applications, very important applications. Essentially, almost everything that you wanted to do before, we can actually do it. So together, we have now a candidate obfuscation, which we can assume or study whether it has this property or not, and a bunch of techniques to show that you can actually do lots of things with it. So today, it's still theory, but like we know in crypto, the theory of today is the practice of tomorrow. So I kind of have a strong feeling that this kind of approach to things will find its way to practice when things become more efficient and accessible. So just to say all kinds of things that you can do with this notion of indistinguishability obfuscation. It's a terrible name, by the way, but never mind, IO. So again, from a cryptographic point of view, you can actually take most of what we know how to do in cryptography, trouble documentations, public encryption, zero knowledge, non-interactive zero knowledge, function, fully homomorphic encryption, never mind. We can actually get all of these from this one primitive, which is IO, plus one functions. And so you can say, okay, what's the big deal? We have a very big hammer, so of course you can do all this, kill all these small flights with it, but still it gives you some understanding. But this is just the beginning. And then from this big hammer, you can actually do lots of things that we didn't know how to do before in cryptography. You can do this very strong form of functional encryption, which is encryption that allows you to give keys said that decrypt only under standard conditions, and which is very useful for cloud security applications. You can do all this multi-party computation, secure multi-party computation in a very simple, non-interactive way. Before, we had to do lots of interactions, lots of rounds of computation. It was very complicated to do and to analyze. Now it's pretty straightforward. You can do concurrent zero knowledge very efficiently. You can do deniable encryption, which is encryption so that you can encrypt things, and later with the police comes to you and asks you, show me, this is the suffix you generated. Show me how you generated. Show me the plain text. You want to be able to text the ciphertext and be able to prove to the police that that the message was any message that you want. It's a very natural property for encryption. We didn't know how to do it before. The question of how to do it was raised 20 years ago, and we didn't know how to do it, and now we know how to do it thanks to this new technique. You can do this delegation that I said before, so I can delegate computation to the cloud, and the cloud can now prove to me that I did this in the right way. You can do it very easily and succinctly. We can actually even get some harness results for game theoretic problems, finding of, prove the hardness of finding Nash equilibria. We can actually do it this way. We can get random workloads on Earth, so those very strong properties for hash functions that before we could we just wanted to, well, the only thing we could do is just assume they exist, or just not even assume they exist, just abstract everything out. Now we can actually prove that they exist, and many more things that are coming up, and maybe your problem can be also solved with obfuscation. But still, there are challenges. There are lots of challenges left with this new and great tool. In fact, many challenges. So, in principle, or general, there are two issues. So one is those tools make very, very strong algebraic assumptions on some algebraic structures, and you want to be able to weaken them, understand them better, try to generalize it. That's as usual, that's what we do in cryptography. Try to get a better understanding of the mathematical hardness that's needed in order to be able to do it. And the other question is how to do this in a more reasonable way in terms of complexity. So the complexity is for normal time, theoretically, but it's really horrendous. It's not anything close to what we would like to be able to do in practice. So there's a lot of work to do here to bring it down. So let me say just a few slides about the second part, because I was more involved in that. So just to say one thing that we know how to do today, this one extra step. So all these algorithms that were developed 2 years ago was obfuscation for what was called a circuit model. So you don't take the program as a program like we know how to do it today. You first take the program, you have to write down the entire Boolean circuit that does the entire program, right? And then you obfuscate that. So for instance, if the program does a binary search over a huge database, you have to write the circuit that does the binary search of the huge database, so the circuit has to be the size of the huge database plus, right? Instead of just have a small program that does it in a normal way. But this is what you could do. And of course, the real world is different. We have small programs that work on big databases. So again, just to make the point that, again, if you take this program and you want to spread it out to a circuit, you have to pay an exponential price from log n to n log n. We would like to get obfuscation for programs, for programs like normal programs that we have today that work on random access machines, and you want the obfuscation to be able to be as short as the program, and the runtime of the obfuscated code should be the same as the runtime of the run program on the actual machine, and the space requirements should be the same, and still it should be secure. And the point is that now we can do it. So we can actually do it. Of course, this is just asymptotic results. The constants are still large. We have to bring them down, but at least asymptotically we have the right complexity. And that's it. And as I said, so I think this is just the tip of the iceberg. There are a lot more to do to understand with this new and shiny tool, how to get it better, how to get more applications from it. But I'm sure you will all hear from it much more in the next years. So thank you.